Hello everyone, I'm Professor Chia-Po Wei. This is the last video lecture for this course. If you have any questions about the course contents, you can contact me or contact the teaching assistants. The quiz on June 15th will be held, but there is no quiz on June 22nd. The solutions of the weekly quiz are posted on the course website. You can take a look when preparing the final exam. The final exam will be held on June 22nd. The time is from 9:10 a.m. to 11:10 a.m. and the scope will cover sections 5.1 up to 5.6. More detailed information about the final exam will be posted both on the course website and on the announcement board of Cyber University. In the previous week, we have covered some results in section 5.5, and in this week we will finish this section. Section 5.5 introduces the concept of orthonormal sets. An orthonormal set is a basis of mutually orthogonal unit vectors. Such a basis is convenient not only in finding coordinates of vectors, but also convenient in solving least squares problems. In section 5.6, we introduce the Gram-Schmidt process. This process allows us to construct an orthonormal basis for a subspace. First, we quickly review the definitions of orthogonal sets and orthonormal sets. Let the set of v1, v2 up to vn be non-zero vectors, and the set is said to be an orthogonal set if different vectors in this set are orthogonal to each other. That is, the inner product of vi and vj equals 0 whenever I is not equal to j. And next, we define an orthonormal set. An orthonormal set is an orthogonal set of unit vectors. A unit vector is a vector whose length is 1. And we know that if u1, u2 up to un is an orthonormal set, then the inner product of ui and uj equals 1 if I equals j, and the inner product of ui and uj equals 0 if I is not equal to j. Given any orthogonal set of non-zero vectors, we can always construct an orthonormal set from the orthogonal set. This can be done by normalizing each vector vi in the orthogonal set to have length 1. That is, we divide vi by its length. Its length is the norm of vi, and we define these new vectors as ui for I from 1, 2 up to n, and u1, u2 up to un will be an orthonormal set. Next, we define what is an orthogonal matrix. An n times n matrix Q is said to be an orthogonal matrix if the column vectors of Q form an orthonormal set in Rn. That is, an orthogonal matrix is a square real matrix with orthonormal columns. If a matrix is not a square, but with orthonormal columns, then we will not call this matrix an orthogonal matrix, because the name orthogonal matrix is only defined for square matrices with orthonormal columns. Theorem 5.5.5 states that an n times n matrix Q is orthogonal if and only if Q transpose Q equals the identity matrix. To prove this fact, we partition matrix Q as Q1, Q2 up to Qn, where Qi is the ith column of matrix Q. And we know that the ij entry of Q transpose Q is Qi transpose times Qj. Because the ij entry of Q transpose Q is the ith row of Q transpose times the jth column of Q, which is Qi transpose Qj. For example, the 1 entry of Q transpose Q is the first row of Q transpose times the first column of matrix Q, and hence Q1 transpose Q1 is the 1 entry of Q transpose Q. Now suppose Q is orthogonal, that is, column vectors of Q form an orthonormal set. Then we have Qi transpose Qj equals delta ij, and delta ij equals 1 whenever I is equal to j, and delta ij equals 0 whenever I is not equal to j. Hence, we have Q transpose Q equals the identity matrix, because the diagonal entries are all equal to 1, and the non-diagonal entries are all equal to 0, which is the identity matrix. Conversely, if Q transpose Q equals the identity matrix, then we have this equality, which means Qi transpose Qj equals delta ij, and this means the column vectors of Q form an orthonormal set, and therefore the proof is finished. We know that Q transpose Q equals the identity matrix implies that the column vectors of Q form an orthonormal set. And because Q is a square matrix, we also have QQ transpose equals the identity matrix. And that is, the row vectors of Q form an orthonormal set in R1 times n. And therefore, we have Q transpose Q equals QQ transpose equals the identity matrix. And hence, Q transpose is the inverse of Q. That is, Q transpose equals Q inverse. We use example 6 to illustrate the orthogonal matrix. The matrix Q is orthogonal because it is a square matrix, and the first column is orthogonal to the second column. And we know that the first column is of length 1, because the square of cosine theta plus the square of sine theta equals 1. And similarly, the second column is also of length 1, and therefore the column vectors of Q forms an orthonormal set in R2, and therefore Q is an orthogonal matrix. It can be also verified that Q transpose equals Q inverse. We have seen this matrix in section 4.1, and the Q can be thought of as a linear transformation from R2 onto R2. The geometrical meaning of Q is that Qx has the effect of rotating x by an angle theta, while leaving the length of x unchanged. And this means qx only changes the direction of x, but the length of x is not changed. To prove this, consider the following two properties. The first property is that inner products are preserved under multiplication by an orthogonal matrix. That is, the inner product of qx and qy equals the inner product of x and y. To prove this property, we know that the inner product of qx and qy equals qy transpose times qx, which equals y transpose q transpose qx. Because Q is an orthogonal matrix, Q transpose Q equals the identity matrix, and therefore we have Y transpose X, and therefore the inner product of Qx and Qy equals the inner product of X and Y. And we will use this property to prove the next property. Multiplication by an orthogonal matrix preserves the length of vectors. That is, multiplication by an orthogonal matrix does not change the length of a vector. To see this, we compute the square of the norm of Qx, which equals the inner product of Qx and itself. And from the first property, we know the inner product of Qx and itself equals the inner product of x and itself, which is the square of the norm of x. And therefore, the norm of Qx equals the norm of x. In this slide, we summarize properties of orthogonal matrices. If Q is an n times n orthogonal matrix, then the following 5 properties are satisfied. Property A: the column vectors of Q form an orthonormal basis for Rn. This is due to the definition of an orthogonal matrix. Property B: Q transpose Q equals the identity matrix. And this result is from Theorem 5.5.5. And property C: Q transpose equals Q inverse. This equality holds because we have Q transpose Q equals QQ transpose equals the identity matrix, and therefore Q transpose equals Q inverse. In fact, not only the column vectors of Q form an orthonormal set, but also the row vectors of Q also form an orthonormal set. Property D: the inner product of Qx and Qy equals the inner product of x and y. That is, inner product are preserved under multiplication by an orthogonal matrix. Property E: the norm of Qx equals the norm of x. That is, the length of a vector is preserved under multiplication by an orthogonal matrix. We have proved properties D and E in the previous slide. The geometric meaning of orthogonal matrices is rotation. The rotation operation only changes the direction of the input vector, but the length of the input vector is unchanged. For example, let's see the right hand side figure. If x is the input vector, then Qx rotates the input vector by an angle theta. And Qx and the length of Qx is equal to the length of x. On the other hand, we have Q inverse y rotates the vector y by an angle negative theta. And note that the length of Q inverse y is equal to the length of y. Next, we discuss Theorem 5.5.6. If the column vectors of A of dimension m times n form an orthonormal set of vectors in Rm, then we have A transpose A equals identity. And the solution to the least squares problem is x hat equals A transpose B. The proof is straightforward, because from the proof of Theorem 5.5.5, we know if the column vectors of A form an orthonormal set, then we have A transpose A equals the identity matrix, and therefore the inverse of A transpose A also equals the identity matrix, and therefore x hat equals A transpose B. We have the following three remarks for Theorem 5.5.6. First, we know that if the column vectors of A form an orthonormal set in Rm, then we must have m is greater than or equal to n, because the dimension of A is m times n, and we can have no more than m linearly independent vectors in Rm. Remark 2. Because the column vectors of A form an orthonormal set, and therefore the column vectors of A are linearly independent, and therefore A has 4 column rank. That is, rank A equals n. And from the result in section 5.3, we know the least squares solution is unique. And we know that the column vectors of A form an orthonormal set is a very strong condition. Usually we do not have such condition. And remark 3 states that in the next section we will learn a method to find an orthonormal basis for the column space of A. And this method is known as QR Factorization. And we can use the QR Factorization to obtain the solution to the least squares problem. Next, we introduce Theorem 5.5.7. Let S be a subspace of an inner product space V, and suppose X is a vector in V, and let U1, U2 up to Un be an orthonormal basis for S. And if P can be written as a linear combination of the orthonormal basis, where the coefficient Ci equals the inner product of X and Ui for each I, then P minus X belongs to S perp. We know that P is the projection of X onto the subspace S. And this theorem states that if P is the orthogonal projection of X onto S, then P minus X belongs to S perp. That is, P minus X is orthogonal to every element in S. We can use the figure in the bottom of this slide to visualize Theorem 5.5.7. If X is a vector in V, and S is a subspace, then if P is the orthogonal projection of X onto S, then P minus X is orthogonal to every element in S. That is, P minus X belongs to S perp. We can use a concrete example to illustrate this. Let X be let the inner product space be R3, and S is the xy plane in R3, and X is the vector of 5, 3, 4. And we know the orthogonal projection of X onto the xy plane is 5, 3, 0, which is denoted by P. And we have P minus X equals 0, 0, 4. And P minus X is orthogonal to every element in the xy plane, and therefore P minus X belongs to S perp. Theorem 5.5.7 is a very important result because it has a wide range of applications. Next, we prove Theorem 5.5.7. First, we show that P minus X is orthogonal to Ui for each I. Then we show P minus X is orthogonal to Y, where Y is any element in the subspace S. To show P minus X is orthogonal to Ui, we compute the inner product of Ui and P minus X, which equals the inner product of Ui and P minus the inner product of Ui and X. Then we substitute the definition of P into the inner product, and we also let the inner product of Ui and X equals Ci, because this is the definition of Ci. And we know that the summation can be taken outside the inner product due to the properties in the definition of inner product. And we know that the inner product of Ui and Uj equals delta Ij, and delta Ij equals 1 whenever I equals to j, and delta Ij equals 0 whenever I is not equal to j, and therefore the first summation equals Ci, and Ci minus Ci equals 0, and hence the inner product of Ui and P minus X equals 0 for each I, and therefore we have proved P minus X is orthogonal to Ui for each I. Next, we will prove P minus X is orthogonal to every element Y in S. If Y belongs to subspace S, then Y can be written as a linear combination of the orthonormal basis. And we compute the inner product of P minus X and Y, and we substitute the definition of Y into the inner product, and the summation can be taken outside the inner product due to properties of inner product, due to properties in the definition of inner product. So we have summation alpha I times the inner product of P minus X and the Ui. Because we have proved that the inner product of P minus X and the Ui equals 0 for each I, and therefore the summation equals 0, and therefore P minus X is orthogonal to y, where y is any vector in the subspace S, and therefore P minus X belongs to S perp, and therefore the proof is finished. Next, we introduce Theorem 5.5.8. Under the hypothesis of Theorem 5.5.7, P is the element of S that is closest to X. And this means if U1, U2 up to Un is an orthonormal basis for S, and suppose P is the orthogonal projection of X onto S, then P is the element of S that is closest to X. That is, for any Y in S and Y is not equal to P, then the length of Y minus X is greater than the length of P minus X. And from Theorem 5.5.8, we know Theorem 5.5.7 is a very important result, because Theorem 5.5.7 allows us to find the element of S that is closest to X, which has a wide range of applications. To prove Theorem 5.5.8, suppose Y belongs to S and Y is not equal to P, and we know that the square of the norm of Y minus X equals the square of the norm of Y minus P plus P minus X. Know that both Y and P are in S, and S is a subspace, so we have Y minus P belongs to S. We also have P minus X belongs to S perp, which is the result of Theorem 5.5.7. Then, because Y minus P is orthogonal to P minus X, then by the Pythagorean law, we have the square of the norm of Y minus X equals the square of the norm of Y minus P plus the square of the norm of P minus X. Because Y is not equal to P, and therefore the norm of Y minus P is greater than 0. Hence, we have the norm of Y minus X is greater than the norm of P minus X, which means P is the element of S that is closest to X, and the proof is finished. Next, we introduce Corollary 5.5.9. Let S be a non-zero subspace of Rm, and B is a vector in Rm. If U1, U2 up to Uk is an orthonormal basis for S, and define the matrix U as U1, U2 up to Uk, which is a matrix of dimension m times k, then the projection P of B onto S is given by P equals UU transpose B. We know that Corollary 5.5.9 is a special case of Theorem 5.5.7, because Rm is a special case of the inner product space V. If V is Rm, then the projection vector P can be computed by matrix multiplication. And we know that if the vector space is not Rm, for example, if the vector space is continuous functions or polynomials, then we cannot apply Corollary 5.5.9. In this case, you have to return to Theorem 5.5.7 to compute the projection vector P. To prove corollary 5.5.9, we know that the projection P of B onto S is given by P equals the linear combination of the orthonormal bases. This is due to the result of Theorem 5.5.7. And because U1, U2 up to UK are vectors in Rn, so P can be written as matrix U times vector C, where vector C is C1, C2 up to Ck, and C1 is the first coefficient, which equals the inner product of U1 and B, which equals U1 transpose B. Similarly, Ck is the case coefficient, which equals the inner product of Uk and B, which equals UK transpose B. And from matrix multiplication, we know this vector can be written as matrix can be written as U transpose times B, where U is the vector defined in the statements of corollary. And now we have P equals UC, and since C equals U transpose B, so we have P equals UU transpose B, and the proof is finished. Next, we use example 7 to illustrate Theorem 5.5.7 and Corollary 5.5.9. Let S be the set of all vectors in R3 of the form x, y, 0. That is, S is the xy plane in R3. And let vector W be 5, 3, 4. And we want to find vector P in S that is closest to W. To this end, first we computed an orthonormal basis for S. Clearly, U1, if we select U1 as E1 and U2 as E2, where E1, E2 are in the standard basis of R3, then U1 and U2 form an orthonormal basis for the xy plane. Then, by Theorem 5.5.7, we can compute the coefficient C1 as the inner product of W and U1, which equals 5. And the coefficient C2 equals the inner product of W and U2, which equals 3. And the projection vector P equals C1 U1 plus C2 U2. And the projection vector P is the element in S that is closest to W. Because the vector space is R3, we can also use Corollary 5.5.9 to compute the projection vector. And from Corollary 5.5.9, we know P equals UU transpose W, where the first column of U is U1 and the second column of U is U2. After some computations, we obtain the same result. We can use the right-hand side figure to visualize example 7. W is a vector in R3, and S is the xy plane. Then the element in S that is closest to W is 5, 3, 0. And we know that because P is in the xy plane, so the z component of P is 0. And we also have W minus P equals 0,004, which is perpendicular to which is orthogonal to every element in S, and therefore W minus P is therefore W minus P belongs to S perp. Next, we discuss example 8. The goal is to find the best least squares approximation to the natural exponential on the interval from 0 to 1 by a linear function. To this end, first we will construct an orthonormal basis for the subspace of linear functions. Then we will apply Theorem 5.5.7 to compute the projection of the natural exponential onto the subspace of linear functions, and the projection is the best least squares approximation that we want to find. Let S be the subspace of all linear functions in the interval from 0 to 1. First, we will construct an orthogonal set, and we know that the functions 1 and the x span the subspace of linear functions, but the two functions are not orthogonal. And to this end, we seek a function of the form x minus a that is orthogonal to 1. To this end, we compute the inner product of 1 and x minus a, which equals the integration of x minus a from 0 to 1, and which equals 1/2 minus a. If we select a as 1/2, then the inner product will become 0, and which means 1 and x minus 1/2 is orthogonal, and therefore 1 and x minus 1/2 forms an orthogonal set. Next, we will construct an orthonormal basis from the orthogonal set. This is straightforward. We just compute the length of each vector in the orthogonal set, and we divided each vector by its length. To this end, we compute the norm of 1, which is also equal to 1. You can verify this fact by yourself. Then we compute the norm of 1. Then we compute the norm of x minus 1/2, which equals the inverse of the square root of 12. And therefore, if we divided 1 by 1, then we obtain u1, which is the first element in the orthonormal basis. And we divided x minus 1/2 by the norm of x minus 1/2, which equals the square root of 12 times x minus 1/2. And this is u2, the second element in the orthonormal basis. Now we already constructed the orthonormal basis. Then we can use Theorem 5.5.7 to compute the projection p of x of the natural exponential function onto the subspace of linear functions. The projection p of x has the form c1 u1 plus c2 u2, where u1 and u2 are the elements in the orthonormal basis, and c1 is the coefficient, which is the inner product of u1 and the natural exponential function, which equals the integration of u1 times the natural exponential function from 0 to 1, which equals e minus 1. And the c2 is the coefficient, which equals the inner product of u2 and the natural exponential, which equals the integration of u2 times natural exponential from 0 to 1. And once we obtain C1 and C2, we have the projection P of x. And the P of x is the best linear least squares approximation to the natural exponential on the interval from 0 to 1. And we visualize the natural exponential on the right hand side figure. We also plot P of x, which is the linear function that is closest to the natural exponential in the least squares sense. In this slide, we review what we have learned so far. In sections 5.1 and 5.4, we introduce the inner product operation. The inner product operation allows us to compute the angle between two vectors. And we can compute the vector projection of one vector onto the other vector. For example, the vector projection of u onto v is a scalar times v, and the scalar is the inner product of u and v divided by the inner product of v and itself. In section 5.5, we learn the concept of orthogonal and orthonormal sets. And we learn how to compute the vector projection of x onto a subspace. If the subspace has an orthonormal basis u1, u2 up to un, then the vector projection is P. P is a linear combination of u1, u2 up to un, where the coefficient Ci is the inner product of x and ui for each I, and P is the element in the subspace that is closest to x. In section 5.2, we learn the concept of orthogonal subspaces, and we also learn the relationship among the four fundamental subspaces of a matrix. In section 5.3, we learn the least squares problem, and we use the following observation to obtain the solution to the least squares problem. Let P be the vector projection of B onto the column space of A. Then we have B minus P belongs to the perp of the column space of A. Then by the fundamental subspaces theorem, we know the perp of Ra equals the null space of A transpose. And from this relation, we can derive the normal equations. And the solution of the normal equation is the solution of the least squares problem. In section 5.6, we will learn how to construct an orthonormal basis from an ordinary basis of an inner product space. This process is known as the Gram-Schmidt process. In this slide, we present some remarks on matrices with orthonormal columns. Let U be a matrix of dimension m times k, where u1, u2 up to uk are columns of matrix U, and suppose u1, u2 up to uk is an orthonormal basis. And we have k is less than or equal to m. Because because U1, U2 up to UK are in Rm, and we know no more than m vectors can be linearly independent in Rm, and therefore k is less than or equal to m. From Theorem 5.5.5, we know that U transpose U equals the identity matrix. However, U transpose uh, in general is not equal to the identity matrix if k is less than m. In fact, UU transpose equals U1 U1 transpose plus U2 U2 transpose plus up to UK UK transpose. You can verify this by yourself. In general, if k is less than m, UU transpose will not be equal to the identity matrix. But if k equals m, in this case, U is a square matrix, and U has orthonormal columns. Thus, U is an orthogonal matrix. And in this case, we have U transpose U equals UU transpose equals the identity matrix. Below is an example of U of dimension 3 times 2. We know that U transpose U equals the identity matrix of dimension 2 times 2. However, UU transpose is of dimension 3 times 3, which is not equal to the identity matrix. We have finished section 5.5, and we will go into learn section 5.6. Recall that constructing an orthonormal basis for an inner product space can speed up the computation of coordinates. That is, if the elements in a basis are mutually orthogonal and each vector is of length 1, then computing the coordinate amounts to computing inner products, which is much faster than solving linear equations. And given an ordinary basis, can we transform it into an orthonormal basis? The answer is yes. In section 5.6, we will introduce the Gram-Schmidt orthogonalization process to accomplish this task. In this slide, we introduce the Gram-Schmidt orthogonalization process. Given a basis x1, x2 up to xn for an inner product space, our goal is to construct an orthonormal basis U1, U2 up to Un such that the span of x1, x2 up to xn equals the span of U1, U2 up to Un. And first, we construct U1 as x1 divided by the norm of x1. And clearly, the span of x1 equals the span of U1. And the U1 is of uni length. That is, the length of U1 is 1. Then we compute the projection of P2 onto the span of U1, and which is denoted by P1. And P1 equals the inner product of x2 and U1 times U1. We know that because U1 is a unit vector, and therefore the length of U1 is 1, and hence P1 equals the inner product of x2 and U1 times U1. And here, the inner product of x2 and U1 is the length of P1. We can use the right hand side figure to visualize x2 and P1. P1 is the projection of x2 onto U1, and and we have x2 minus p1 is orthogonal to u1. And this is a result from Theorem 5.5.7. And we know that x2 minus p1 is not the zero vector because x2 minus p1 is a linear combination of x2 and x1. We know that x2 minus p1 is x2 minus some scalar times x1, and hence x2 minus p1 is a linear combination of x2 and x1, where the coefficients are not all zeros, and therefore x2 minus p1 is not the zero vector. Because if x2 minus p1 is the zero vector, then we find some non-zero coefficients such that the linear combination of x2 and x1 equals the zero vector, which is a contradiction to the fact that x1 and x2 are linearly independent. Because x2 minus p1 is not the zero vector, the length of x2 minus p1 is not zero, and we can define u2 as x2 minus p1 divided by its norm. And we know that x2 is a unit vector because the length of u2 is 1. And u2 is orthogonal to u1 because x2 minus p1 is orthogonal to u1. And from the above, we know span of u1, u2 is a subset of the span of x1, x2 because u1 and x1, because u1 equals x1 divided by its norm, and u2 equals x2 minus p1 divided by its norm, and x2 minus p1 is a linear combination of x1 and x2. Therefore, the span of u1, u2 is a subset of the span of x1 and x2. And we also have u1 and u2 are linearly independent because u2 is orthogonal to u1. They are mutually orthogonal, so u1 and u2 are linearly independent, which means the dimension of span u1, u2 is 2, and therefore we have the span of x1, x2 equals the span of u1 and u2. We continue in the same manner to construct u3. Let P2 be the projection of x3 onto span of x1 and x2, which equals the span of u1 and u2, which is proved in the previous slide. And because u1, u2 forms an orthonormal basis for the span of x1 and x2, then we can apply Theorem 5.5.7 to obtain the projection P2, which is C1 U1 plus C2 U2, and the coefficient C1 equals the inner product of x3 and U1, and the coefficient C2 equals the inner product of x3 and U2. We can use the figure in this slide to visualize P2. P2 is the projection of x3 onto the span of u1 and u2. And we know that x3 minus P2 is orthogonal to the span of u1 and u2. Also know that the norm of x3 minus P2 is non-zero because x3 minus P2 is not the zero vector. We can use a similar reasoning as in the previous slide to show that x3 minus P2 is not the zero vector because x3 minus p2 is a linear combination of x1, x2, and x3. And because x1, x2, x3 are linearly independent, their linear combination cannot be equal to the zero vector. Otherwise, this will contradict the three vectors are linearly independent, and therefore x3 minus x2 is not the zero vector, and we can define u3 as x3 minus p2 divided by its norm, and continue in the same manner. We can construct u1, u2 up to un such that the span of u1 up to un equals the span of x1 up to xn, and the Gram-Schmidt process is then complete. Theorem 5.6.1 formally describes the Gram-Schmidt process. Let x1, x2 up to xn be a basis for the inner product space V, and let u1 be x1 divided by its norm, and define u2, u3 up to un recursively by uk plus 1 equals xk plus 1 minus pk divided by its norm for k from 1, 2 up to n minus 1, and let pk be the projection of xk plus 1 onto the span of u1 up to uk, and therefore the projection pk is a linear combination of u1, u2 up to uk. Then the set u1, u2 up to un is an orthonormal basis for V. We use mathematical induction to prove Theorem 5.6.1. Suppose u1, u2 up to uk have been constructed so that u1, u2 up to uk is an orthonormal set, and the following condition is satisfied. That is, the span of u1, u2 up to uk equals the span of x1, x2 up to sk. We want to prove that if uk plus 1 is constructed in the same manner, and we need to prove the span of u1, u2 up to uk plus 1 equals the span of x1, x2 up to xk plus 1. And recall that pk is the projection of xk plus 1 onto the span of u1, u2 up to uk, and therefore the projection pk is a linear combination of u1, u2 up to uk, and since we have the span of u1 up to uk equals the span of x1 up to xk, and we know pk belongs to the span of x1 up to sk, and hence xk plus 1 minus pk belongs to the span of x1 up to sk plus 1, and therefore sk plus 1 minus pk is a linear combination of x1, x2 up to sk plus 1. And since x1, x2 up to xk plus 1 are linearly independent, and because xk plus 1 minus pk is a linear combination of x1 up to sk plus 1, and the coefficient of the linear combination are non-zero, and therefore we have sk plus 1 minus pk is not equal to the zero vector. And we also have sk plus 1 minus pk is orthogonal to each ui for I from 1 to up to k. And this is because sk plus 1 minus pk is orthogonal to the span of u1, u2 up to uk. And this condition implies that sk plus 1 minus pk is orthogonal to each ui for I from 1 to up to k. And because sk plus 1 minus pk is not the zero vector, and hence we can define uk plus 1 as sk plus 1 minus pk divided by its norm. And we have u1, u2 up to uk plus 1 is an orthonormal set because uk plus 1 is orthogonal to each ui for I from 1 to up to k. And we also have u1, u2 up to uk is in the span of x1, x2 up to xk plus 1 because uk plus 1 is a linear combination of s1 up to sk plus 1. And therefore u1, u2 up to uk plus 1 is a subset in the span of x1, x2 up to xk plus 1. And since u1, u2 up to uk plus 1 is linearly independent because the vectors are mutually orthogonal, which implies linear independence, and therefore we have the span of u1, u2 up to uk plus 1 equals the span of x1, x2 up to sk plus 1, and the proof is finished. We use example 2 to illustrate the Gram-Schmidt process. Let the columns of matrix A be A1, A2, and A3, and suppose A1, A2, A3 are linearly independent, and our goal is to compute vectors Q1, Q2, and Q3 such that they form an orthonormal basis, and the span of Q1, Q2, and Q3 equals the span of A1, A2, and A3. And this can be done by the Gram-Schmidt process. First, we compute Q1, which equals A1 divided by its norm, and we denote the norm of A1 by R11, which equals 2. After we computed Q1, then we can compute P1, which is the projection of A2 onto span of Q1, and P1 equals R12 Q1, where Q1 is the inner product of where R12 is the inner product of Q1 and A2. After we obtain P1, we can compute A2 minus P1. And A2 minus P1 is a non-zero vector, and therefore we can compute Q2 as A2 minus P1 divided by its norm. Its norm is denoted as R22, which equals 5. Once we obtain Q1, Q2, then we can compute the projection of A3 onto the span of Q1 and Q2, which is P2. And P2 equals R13 Q1 plus R23 Q2, where R13 is the inner product of Q1 and A3, and the R23 is the inner product of Q2 and the A3. Once we obtain P2, we can compute A3 minus P2, which is a non-zero vector, and we can define Q3 as A3 minus P2 divided by its length R33. And the vectors Q1, Q2, Q3 form an orthonormal basis for the column space of A. Next, we introduce Theorem 5.6.2. If A is of dimension m times n, and suppose A has rank n, then the column vectors of A are linearly independent, or we can say A has 4 column rank. Then A can be factored into a product A equals QR, where Q is a matrix of dimension m times n, and the column vectors of Q form an orthonormal set. And matrix R is a square matrix of dimension n times n, which is upper triangular, and the diagonal entries of R are all positive. We know that the matrix R must be non-singular because its diagonal entries are all positive, and it is diagonal, and it is upper triangular. Therefore, the determinant of R is greater than 0, and hence R is non-singular. The proof of Theorem 5.6.2 is skipped, and we will use example 3 to illustrate Theorem 5.6.2. We use example 3 to illustrate how to use the Gram-Schmidt process to obtain the QR factorization of matrix A. First, we compute Q1, which equals A1 divided by its length, and we know A1 equals R11 Q1. And following similar procedure as in the previous example, we have Q2 equals A2 minus P1 divided by its length, and therefore we know A2 equals R22 Q2 plus P1, and because P1 equals R12 Q1, and therefore A2 equals R22 Q2 plus R12 Q1. And following similar procedure as in the previous example, we have Q3 equals A3 minus P2 divided by its length, and therefore A3 can be written as R33 Q3 plus P2. And because P2 equals R13 Q1 plus R23 Q2, and hence A3 can be written as R33 Q3 plus R23 Q2 plus R13 Q1. And we know that the equality in green colors. For example, A1 equals R11 Q1, which is matrix Q times the first column of matrix R. Because A1 equals R11 Q1, which is matrix Q times the first column of R. And we also have A2 equals R22 Q2 plus R12 Q1, which is which is matrix Q times the second column of matrix R. And we also have A3 equals R33 Q3 plus R23 Q2 plus R13 Q1, which equals matrix Q times the third column of matrix R. And therefore we have A equals QR. We know that matrix A and matrix Q have the same dimension, while matrix R is an upper triangular matrix, and whose diagonal entries R11, R22, R33 are all positive, because R11, R22, and R33 are the norm of a vector, and the norm is positive, and hence the diagonal entries of R are all positive. After we substitute the values of Q1, Q2, Q3 into Q, and substitute the values of R11, R12 up to R33 into R, we obtain the QR factorization of matrix A. In this slide, we illustrate Theorem 5.6.3, which uses the QR factorization to obtain the solution of the least squares problem. Let A be a matrix of dimension m times n, and suppose A has 4-column rank. Then the least squares solution of Ax equals b is given by x hat equals R inverse times Q transpose B, where QR is the QR factorization of A obtained in the previous theorem. Or we can obtain the least squares solution by using back substitution to solve Rx equals Q transpose B. To prove this theorem, we know that if x hat is the solution of the least squares problem, then x hat satisfies the normal equations. And if A equals QR, then we substitute A with QR into the normal equations and obtain QR transpose QRX equals QR transpose B, which can be written as R transpose times Q transpose Q times Rx equals R transpose Q transpose B. Because Q has orthonormal columns, and we know Q transpose Q equals the identity matrix. Hence, the above equation becomes R transpose Rx equals R transpose Q transpose B. Because R is upper triangular and R is non-singular, and therefore the last equation simplifies to Rx equals Q transpose B. We know that R is an upper triangular matrix, and Q transpose B, the values of Q transpose B are known, and x is the variable that we want to solve. And because R is upper triangular, we can use back substitution to obtain x, or we can compute the inverse of R and perform matrix multiplication to obtain x, and the proof is finished. Note that the modified Gram-Schmidt process in page 289 is not in the scope of the final exam. Thus, you can skip page 289 when preparing the final exam. I have selected some exercises for sections 5.5 and 5.6. You can use these exercises to test whether you understand the course contents. In this week, we have learned how to compute the projection of a vector x onto a subspace with an orthonormal basis, which is P. P is the element in the span of the orthonormal basis that is closest to X. And we also learn the Gram-Schmidt process. Gram-Schmidt process can be used to construct an orthonormal basis. I hope this video provides you a better understanding of orthogonal and orthonormal sets and their applications. If you have any questions, do not hesitate to ask.